2 minutes past 4, time to do some work. Okay, so this is what we're going to be doing today. I take it by now everybody's in the right room. Just give you a quick introduction. This is me, my name's Gary Short. I'm a Microsoft MVP, freelance data scientist, big data architect and engineer. Usually using these kind of tools here, HD Insight, Hadoop, Pig Hive, that kind of stuff. Now, data science is a broad church. It covers a lot of things. What I actually specialize in is predictive analytics, which I did on Tuesday, and a little bit yesterday. Machine vision, which I'm not doing at all this week, and computational linguistics, which does kind of feature in what we're doing here, but we're not actually going to talk a great deal about it because we can disappear down that rabbit hole very, very quickly. So we're kind of gloss over the computational linguistics part in this. Most important part of this slide is the bit down at the bottom there where you see my blog, my email address, and my Twitter handle. Please feel free to email me or tweet me or follow me with any questions that you might have after this session. So that's me. What about you guys? How many of you guys have done any kind of data sciencey stuff before? No? Okay, a couple of people have. All right. The samples in this session are going to be in Node and F#. Anybody done Node before? Yep, a couple of people. Anybody done F# before? Okay, a couple of people. Unfortunately, different people. So it's all going to be cool. There isn't going to be anything earth-shatteringly difficult in any of the code we look at. Okay, so I'll walk you through the code. It'll be really simple. Any programmer should be able to follow it. Don't be scared with it being F#. Having said that, you should be very scared of my F# code. Okay, especially if you are an F# programmer. So this is what we're going to cover in the next 90 minutes. We'll define the problem that we're going to tackle, okay, and then we'll have a look at a way of solving the problem. There are lots of different ways of solving it. We're going to pick one, and we're going to solve that problem. Then I'm going to do a little bit about having a little bit of fun with the trolls, something that we're going to talk about hypothetically, of course, something that I would never actually do, something that I don't recommend you ever do, all right, but we'll look at it from a hypothetical point of view. And then at the end, we might, depending on how much time is left, we'll have a lot of discussion about something a little bit more sinister than just trolling and how we could adapt what we've learned whilst we solve the problem of trolling to this new kind of sinister problem that we're going to talk a little bit about at the end, depending on how much time we've got. So first of all, defining the problem. What is it that we're actually talking about here? So we're talking about trolling, and trolls, some of them are just purely insulting. So here was one that was sent to Rebecca Adlington. You know, you shark-fin-nosed blank, you belong in that pool, you blank whale. Right? Well, that's not very nice. Okay, so we're talking about stuff like that. Some of it's actually threatening. Okay, there's you can see here, dirty little girl like you should keep quiet, otherwise we'll publish your back history. This is something that's come about just recently. I've kind of noticed there's a word for this and I've completely forgotten what it was because I'm a trained professional. I should have that on the tip of my tongue. Unfortunately, I've forgotten what it's called, but it's basically when a bunch of hackers get together, they target somebody and they go back through like your bank records and your hospital records and your birth records and stuff like that, and they create a document of everything about you, and then they publish that on the internet. You know, they threaten you, if you don't stop doing what you're doing, or you don't keep quiet, or if you say that thing again, then we're going to publish all this documentation about you. Okay, and that's become a new thing. That's slightly more than just trolling, but you'll find that the trolls will threaten that kind of thing, even if they don't really have the technical skills to bring it about. If you are a politician, or if you are speaking against a politician or something like that, or you're in the public eye and you get a threat, similar to that kind of thing, that's likely to give you pause to think, because you can never tell just from that whether this guy is just a troll threatening that thing in the same way as other people, threaten to come around and burn your house down. There's no real threat of that ever happening. You have no real way of knowing whether they do have the technical skills to be able to do what they're threatening here. So regardless, it's still quite scary to see. Some of them, of course, are really threatening. Okay, this is one that was sent to Jessica Innes. Saying to remove her name if Ched Evans is saying, I hope he rapes her, right? Well, that's got to be a horrendous thing to be on the receiving end of. Some of them come from an army of trolls, not necessarily threatening in and of themselves, but the sheer majority of them. This is actually something that happened this week. This guy, I'm not entirely sure how you pronounce his name. I would say it's Oisin Timon. This was the guy that Jeremy Clarkson punched and got sacked from the BBC for. You can see there's a bunch of fans here of Jeremy Clarkson when this happened, got onto Twitter, and the things that were sent to him kind of range from, you know, I can't believe you made such a fuss just because somebody slapped you, you're such a girl, right down to down here, you know, aren't you dead yet? Which is got to be no fun at all to receive that kind of thing. So all of that kind of thing all comes under trolling, and you can see it's variously bad. There's something else that I noticed. Some of them are actually quite eloquently put. You know, no wonder they have a like mind to you. You are a siren of treachery and on demagoguery. Repent, right? Just because you use big words and you're nice about it, right, doesn't mean to say it's not trolling. Okay, just because you're an educated troll, you're still a troll. This is something that I came across quite recently as well. So this is some are actually state sponsored. Now, before I get into this, I'm actually going to name a political party here. I'm not taking any political sides. I'm absolutely positive that every single political party is just as bad as the item I'm about to describe to you. And the only reason I'm using this one is because it's only just happened. The next time I give this talk in a few months' time, something else will have happened and it'll be another political party. I'm absolutely sure they're just as bad as each other. But when I say state-sponsored, what I mean here is this particular instance of trolling was quite an interesting one, because it's the first time that I've noticed, I'm not saying it's the first time it's ever happened, but it's the first time I've noticed the kind of political parties and people in the public eye, organizations in the public eye, kind of using trolling, not necessarily using trolling because they weren't controlling it, but allowing trolling to kind of mask something that they've done that they don't really want the public to find out about, and the whole barrage of trolling is keeping that noise down. So what this particular story is about, and I've put this up here so you can go back and check it out later, but what happened here was Nicola Sturgeon, the First Minister of Scotland, was invited to the service of remembrance that they had for the British troops a couple of weeks ago, all right? And she didn't go. She turned down the invitation. And a lot of unionist supporters in Scotland started to tweet about, you know, how disrespectful that was, you know, and even if she didn't believe in the war, and even if she actually believed it was an illegal war, if that was the frame of mind that she was in, at the end of the day, she's representing the people of Scotland. She's the First Minister of Scotland. She should have gone, and that was the kind of thing that they were protesting about. And immediately there was a big storm of trolls, of people supporting the SNP, who started to write, well, Nicola Sturgeon didn't go because she was at the commemoration for the Dunblane massacre, you know, and how dare you politicise such a thing, the death of small children, you know, just to score political points. That's absolutely terrible. And that kind of made all of that sort of negative publicity for the SNP go away, because, you know, this big sort of army of people were making what is quite a valid point. Until some people started to text back, to tweet back and say, well, look, I don't really have a political axe to grind here, but I happen to know that she wasn't at that memorial service because I was at a political meeting and she was one of the speakers. Okay, and then immediately the trolling all started again, and there was a big kind of, you know, flame war going on, and all these trolls were kind of pushing down, you know, that kind of news that, well, actually that didn't really happen. And it wasn't until people who were at that meeting started to actually tweet photographs of the First Minister at this meeting, that at that point all the trolls ran out of ammunition, obviously, at that point, because there was no argument to be had. It's like, well, here's photographic evidence. They all drifted away, and it was at that point that the SNP then released a statement to say, no, Nicola Sturgeon wasn't at any memorial, she was actually at this political meeting. But it's kind of clear that political party, and I'm not picking on them particularly because I'm sure they're all just as bad, but that political party were using the trolls that were surrounding their organisation to actually, you know, dampen down that negative publicity. And it wasn't really until they couldn't do that anymore that they kind of came clean, kind of thing. And that's the first time I've seen, you know, trolls. They're not being used, because I'm not saying that any political party controls trolls, but they could have immediately stopped that kind of abusive behaviour if they just made the statement, you know, much, much earlier. This has gone on for days before they actually came out and made the statement. So it's not that they're using the trolls, but they're allowing the trolling activity that happens anyway for their own purposes. Okay, and that's the first time I've seen that, and so it's something I'm going to be watching more of, because I think, especially in the run-up to the general election and elections, you know, after this and referendum after that and all the rest of it, that with political parties becoming more observant about what happens in social media, you're going to see this kind of thing a lot more, I think. So that's the kind of thing we're talking about. Next thing we want to talk about is really, are trolls dangerous? You know, I mean, is it really just text, or are they actually dangerous? So here's a couple of studies that were done, right? And they looked at these number of people, and then the investigators found that internet trolls tended to have the personality traits related to sadism, psychopathy, and Machiavellianism. So the answer to that question is yes, they probably are dangerous, but not really to you, right? They're probably dangerous to, you know, the people who are close to them, who come in contact with them, you know, every day. If you exhibit these kind of traits, you know, that you're kind of on a continuum from an annoying kind of person that nobody really likes, especially if you're quite Machiavellian, right up to, you know, if you actually are, you know, displaying sadistic tendencies and stuff like that, quite dangerous. But really, not to you if you are receiving it's upsetting, but actually it's probably not dangerous. Although these people are quite dangerous themselves, the anonymity of the internet and the fact that they're probably miles away probably means that they're not dangerous to the people they're trolling, although they are probably quite dangerous to people around about them. So, how are we going to solve this problem? Right, that's what we're going to look at right now. So, how we're going to do that is pretty much the same way, actually, is spam is solved already. Okay, because when you think about it logically, it's the same problem. Okay, so the difference between spam and ham is spam is you know, spam email that you don't want, ham is good email that you do want. And at the minute, the latest statistics that I saw said that about 98% of the emails out on the internet are spam. The vast majority of these get culled long before they get to your inbox, okay? Your inbox does not contain 98% spam email, okay? There are one or two that still manage to get through because, you know, there's a continuing kind of arms race between the spammers and those who are trying to control spam, all right? So there's never an out-and-out victory. Well, there's not an out-and-out victory at the minute, but far less than 98% of the emails that you receive are going to be spam. So the solution that is in place for email is kind of working right now, okay? And that's the model that we're going to go with. So how we're going to do that is pretty much the same way as email spam is taken care of. So what we're going to do is, so we're going to imagine that it's our responsibility to remove troll posts, which from now on I'm going to just refer to as spam, okay? We're going to remove spam. It's our job to remove spam from any given person's Twitter stream. Okay, so how we're going to do that is we're going to hook up a process to the Twitter API and capture that tweet stream before it arrives in the client. And then what we're going to do is we're going to decouple that processing from the capturing, okay, so that no processing actually occurs on the listening thread, and we're going to talk about that, why we do that when we get there. And then the last thing we're going to do is we're going to construct, and we're going to use machine learning to construct a Bayesian classifier which will actually classify each of the tweets that comes in as either being spam or ham, and it will let the ham ones through and will do something, either throw it away or quarantine it, and we'll talk about that later, with the actual ones it identifies as spam, letting the ham ones back into the process. So that's basically the process that we're going to use. We're just going to inject a process into the pipeline that exists at the minute and do some Bayesian classification to work out which is good and which is bad. Okay, so first of all, what we need to do, enough talking, let's look at some code. We need to hook up to the Twitter process, okay? So, jump down here and have a look at some code. If I open this up, this is where I like to start. It's the simplest thing that'll work. Okay, so what we're doing now, this is a nice piece of Node script. I like to use Node for lightweight processes that just kind of run as daemons on a machine that I've got at home. You know, they take up hardly any processing, hardly any memory. They're very good for this kind of thing. So lightweight services on the internet I like to use Node for. And what we've got here, unfortunately I have left my slide advancer at home, so I'm down to the old-fashioned pencil. What I've got here right at the top is we bring in a couple of packages that we're going to use. One's called util, which allows us to write out to the console. The other one is, actually that isn't true. That's for a piece of code that I don't need anymore. It's for debugging, so I should have actually removed that. But we bring in the Twitter client here because there's no point in reinventing the wheel. There are plenty of Twitter clients out there. So I bring in this Twitter client here. Then what we do is we actually instantiate the new Twitter client. We put in your consumer key, your secret, and your token key and token secret. Those are some things that you will get from Twitter when you set up an application. You have to say to Twitter, I want to use an application to use the API. This is, and you make a description of your application. At the time that you do that, you get these pieces of information here from Twitter, and you just paste it out of the dev site for Twitter, and copy them out of the dev site for Twitter, paste them in here, okay? And then once we've done that, what we say is, I want to use the streaming API, Twitter, and I want to use a filter, and I want to try everything that's sent to GarageDoor, right? So I'm tracking everything that's sent to me right now from the streaming API. And what this does is it's a callback, because as we know, Node is completely asynchronous. So what we've got here is a callback, and it says, I want to listen for data, right? And when data arrives, all I want you to do is to write it out to the console, okay? Which doesn't seem to be doing anything, all right? But obviously what we want to do is we want this to be up and running, and we also want to be able to restart it when, from time to time, Twitter will close this connection from their end. And they do that for a number of reasons. The most likely reason that your listener has to restart is because the Twitter shard that you're listening to has just died, okay? And therefore you lost your connection and you need to reconnect, okay? So what we're going to do is, this is the simplest thing that will work here, but we need something to actually start it up, and we need something to restart it if it dies, and we need something to deal with the fact that we've just written it out to the console, and we need to capture that somewhere. So the tool I use for doing that is a nice little tool called Upstart, which, if it's not in your Linux or Unix-like operating system by default, you can apt-get in, or you can brew in or port in, or whatever is your favorite way of getting software onto your machine. But what it allows you to do is to basically define how you want daemons to work, okay? So basically this line here says, when we have a file system in a network, because there's no point in starting it if the file system doesn't come up, and if the network doesn't come up, there's no point in starting it, because without the file system and without the network, then there's nothing for our listener to do, okay? But once those things are up, then what I want you to do is start, okay? And I want you to stop when the system stops. So this process will be shut down as the machine shuts down, okay? So you'll be able to shut down your listener gracefully. This is the key part here, this respawn. What happens here is every time Twitter shuts you down from its end, okay, it will restart. Okay. Now, as I say every time, actually it'll only respawn 5 times. If there's an error here, like for example, I pasted in the wrong key, for example, and I'm getting an authentication failure, it won't sit there all day hammering away at Twitter going, can I use the API? Twitter goes, no. Can I use the API? Twitter goes, no. All day. It won't do that. What will happen is, if it gets into that kind of start-stop cycle, it'll only respawn 5 times in a row. Okay, and after that, it's going to go, do you know what? Your code's just broken, or the network's gone down, or something like that. Okay, and it'll stop after 5. So you're not going to get blocked by Twitter's terms of use and stuff like that, because it'll only try 5 times and then it'll give up. And then down here is the exec. It's actually the thing you want to actually run. And what we're saying here is, I want you to run the listener, and here you say, I want to append the output from this listener just into this results file here. And that's how we deal with the fact that in the actual code, we're just writing out to the console. Okay? This line here says, stuff that gets written out to the console, append it into this file here. Okay? Note the use of the double arrow, not the single arrow, so it's not a rewrite, it's an append. So if you are respawning, it'll append to the end of what's already there, it won't overwrite. So you'll continue to get the input, and it'll just rattle on into that file until you tell it to stop. Okay? Right, any questions about that? This is the simplest thing that'll work, and I use it quite successfully for small data science projects. So if I want to capture, the last thing I did, if you read my blog, I've been doing some data science stuff on, the budget was the last thing that I was looking at. So, if you're looking at the budget, all the tweets that were made about the budget on that day, this is a nice little thing for, catching like 1 or 2 days worth of work, okay? Any questions about the code I've shown you so far? pretty straightforward. Like I said, don't panic if you're not a Node programmer. We're not going to be doing anything difficult. Okay, so let's jump back to the slides then. That's all fine and good for short-term stuff, okay? But Twitter does have a set of best practices, right? Most importantly, it's got this. It's got back-off strategies. It's going to say to you, during the time that you're either trying to connect or when you are connected, various things will happen. And you have to back off different ways depending on what has happened, okay? And Twitter lays down how it wants you to do that. Okay, so that's one of the first things. The other thing here is it talks about the fact that if you fall behind, if you're not processing the tweets fast enough as it's sending them to you, you'll get a stall warning, right? And if you don't respond to the stall warning, i.e. speed up by, basically processing the tweets faster, then after a while it gives you a stall warning. If you're still falling behind, it will just terminate that connection. Okay, so we have to deal with that stall, we have to deal with the stall warning kind of thing. And actually how we deal with it is just to do no processing whatsoever on the listening thread. Okay, so all the listener is actually going to do is to take the tweet, don't do any processing with it whatsoever, and just put it on a queue. Right, so it goes, there's one, there's another one, there's another one, there's another one. And something else is going to consume that queue and do all the processing. So that's how we're going to decouple the listening from the actual processing of the tweets. So at no point really can we fall behind in the actual listening of the tweets because we're doing more and more complex processing of those tweets, because we're not going to do them on that thread, right? We're going to get that listener just to pump stuff onto a queue, and we'll come back and we'll consume that queue later, right? But if you're doing anything more than just a day or two's worth of trawling of tweets, then you want to follow this if it's something that you're going to be using long term. Like you want to follow, what the basic sentiment of the population of the UK is over the year, and you're actually going to capture, a year's worth of tweets. You want your listener up and running for that whole time. So we need to follow them really. So what we're going to do is we're going to go back and we're going to look at, here we looked at, this is the simplest thing that works. But what we actually want is something which will adhere to all the best practices and everything, and we can have it running for forever basically. So it's a little bit more complicated, right? But it isn't too bad actually. So it's quite similar. So here you can see I require in the files that I require in the libraries that I need. You can see me bringing in the Twitter one again. This time I'm going to bring in a library called AMQP, which allows me to use a message queue, and that's where I'm going to put my tweets. So that's what that does. Then I'm going to abstract away a path so that I can actually have my path abstracted, and I'm going to have a configuration file where I can put my configuration stuff, keep that separate from my file. And I'm going to start doing some logging actually, because if I'm going to have this thing up and running for a year, chances are some edge case error is going to happen. So what I'm going to do here is I'm going to start at main there. I'm going to log the information that I've actually started, and then what I'm going to do is I'm going to say, go find me my configuration file, okay? And if the configuration file is not present, then you may as well throw an error at this point and stop, because I can't do anything without a configuration file. If I do have the configuration file, then go ahead and do that callback. The configuration file there basically says read the configuration file. If there's any problems, then error out. Validate that configuration file. So down here what we do is we make sure that everything that I expect to be in that configuration file that I need is actually there, because again there's no point in continuing if I don't have authentication information and stuff like that in it. So what I do there is I just basically make sure all of that stuff that I need is actually available, and if it's not, then I error out. Otherwise I'm gonna run that callback. And that callback is going to say, right, what I want you to do is establish a connection to, at this point, it's RabbitMQ server, but it could be any messaging server of your choice. It doesn't really matter. So what I do there is I log on to the queue at that point. Again, if there's any problems, I error out. Otherwise, once I get a connection, I set up the queue. I give it a name, tell it it's going to be durable, auto-delete, exclusive, all that good stuff. And then, again, I run a callback once I've got that going, which basically says, now that I've got a connection to my queue and I can actually put stuff onto the queue because the queue's there, it's time to instantiate the Twitter client. So I instantiate the Twitter client just using that exact same code that you've already seen before, okay, just with all of my credentials, which I will get from Twitter, and I set up Twitter. There's that same code again where I've got that stream. So I'm streaming all tweets coming to myself. If there's any problems there, again, I log it and leave. Again, once the stream is closed, I log that information. Once we've got it actually up and running, then what I want to do is if we get an actual timeout. So here, once we've got it up and running, then we're going to do that same thing. Instead of at the point in the old code where I was getting data, I just wrote it out to the console. Here, we're posting it to the queue instead. Okay. Now, other things are going to come down. Other things are going to come down the pipe, and one of these things, what we're going to have to do is just scroll past all the logging stuff. Is get the milliseconds that we have to wait if our connection failed or our connection was broken. And as I said, the Twitter best practices, which are documented here if you want to go and read them, actually tell you how to back off. So what we're going to do here is, if there's no status code, all right, then we're going to assume it's a TCP IP error, and we reconnect immediately, adding 250 milliseconds after each attempt, because that's what they say to do. So that's what that code does. For HTTP errors other than a 420 error, okay, what Twitter tells us to do is start with a 5-second delay and double that delay after every attempt up to a maximum of 320 seconds. Once you reach 320 seconds, Twitter is quite happy for you to retry every 320 seconds. You don't have to keep the delay going forever. 320 milliseconds, it's happy with. Okay, so that's what that code does there. That's for errors other than a 420. For errors which are 420 errors, then what we want to do is we need to wait a minute, and then we double each time indefinitely. Okay, and that's what that code does there. And really, that's the rest of it. The rest of it is just tidying up our constants for times to waits and things like that. So as you can see, the kind of more advanced one that you can have running basically all year is quite robust. Okay, it deals with Twitter's problem with you not keeping up by not processing anything on the thread, pushes it off to a queue, and it completely implements everything that Twitter wants you to do in terms of backing off. Okay, so you would use this version of the code or something like this version of the code if you wanted your Twitter listener running forever, which is basically what we want to do if we are going to solve this problem of trolling. We know a day or two is no use to us. We're going to want this thing running all the time, so it needs to follow these best practices. Any questions about that? Nope. All right, good. Let's jump back into our slides then. Let's have a look and see how the time's going. Good. So as this is adhering to best practices. Now what we want is, we're at this end just now where we've pulled the tweets from Twitter and we've pushed them onto a queue. What we need to do now is have a consumer that consumes that queue and actually deals with the tweets, the processing of the tweets. So this is how we're going to do it. This is basically Bayes' equation, which looks kind of horrible when you see it written down, all right? But actually, it's very straightforward once you get it explained to you. So what this actually says, this is the formula that we're going to use for our machine learning classification, and what it basically says is this. It falls down into a number of parts. The first part is this. This is called the posterior probability, and it's what we're actually going to calculate. And what it says is, how probable is this event given that that event has already happened? So in our case, it's going to be, what is the probability of this tweet being spam given that it contains this word? Okay, so that's how you read that bar, given that. All right, so the probability that this tweet is spam given that it contains this word. That's the posterior probability. To calculate the posterior probability, the first thing we do is we calculate this likelihood function. And this likelihood function is how probable is the evidence given that our hypothesis is correct. Okay, and our hypothesis at this point is that it is spam. So what this basically says is, what is the probability of seeing the word we're looking at, given that the tweet is spam? So basically, how often does that word appear in spam tweets? Okay, that's our likelihood function. The next thing over here is called the prior probability. And it tells you how probable was the event before any evidence. So basically it says, regardless of the evidence that you've given me, how probable is the event to happen anyway? Okay, so in this case, it's going to be, how probable is it that we get spam? Regardless of what words are present, you know, for any given tweet that we get, what is the probability that it's spam anyway? And that's the prior probability. The prior probability. And the last thing here is called the marginal probability. The marginal probability is how probable is the evidence under all possible hypotheses. Okay? And what that basically means is, how probable is it that we see this word regardless of it being spam or regardless of it being ham? Okay? So how prevalent is that word in the tweets that we get regardless of whether they're ham or spam? And that is called the marginal probability. Okay? That's all kind of horrible, right? I've kind of explained it the best I can. It's all kind of abstract. The best way to look at this actually is to do an example. So let's work our way through an example. Before we do that though, let's just do this by intuition, because one of the things about probability in data science is to have a good intuition of the probabilities before you actually do the math. So what we're going to do now is imagine a new dread disease exists, okay, and it's completely fatal, 100% of the time. If you get this disease, you die, that's the end of the story. The good news is there's a test for this disease, and the test is 99% accurate. The question is, you test the prevalence of this disease is 1 in 100,000 in the population. So 1 in 100,000 of the population is going to get this disease. If you get it, you die, there's no cure. There is a test, the test is 99% accurate. And the question is, given that you test positive for the disease, should you be worried? Okay, so put your hands up if you think you should be worried. You test positive for this disease, it's 99% accurate, totally fatal. Hands down. Put your hands up if you think it's not a big problem. Okay, cool. Why do you think it's not a big problem?
Because there's such a small chance you're going to get the disease. You're kind of playing the numbers. There's a likelier chance that you're the 1% of the inaccurate test than it is you've got the disease overall. Okay,
so and who thinks you would be worried if you got a positive test? Put your hands up if you were worried before. Okay, and why would you be worried if you got a positive test?
Because that chance is 99%.
Because the test is 99% accurate. Yeah. There's only a small chance that it's wrong. So both of those sound reasonable, right? Gentleman here says, doesn't really matter if it's positive or not. There's such a low chance of you actually having the disease, there's actually a better chance that the test is wrong. On the other hand, that sounds reasonable, but on the other hand, they say, well, the test is 99% accurate. So if you get the test and the test is positive, it's 99% accurate. So, you know, that sounds reasonable as well. And it's because intuitively, both sides of that argument seem intuitively correct, that probability can be quite difficult sometimes. So the best way to do it is actually, you know, to do the maths. And we're going to use this maths here, but we're going to make it easy by drawing a diagram at the same time, because that will make it easy for us to do the maths. So if we start here and we say, right, probability of having the disease and not having the disease. So there's a 1 in 100,000 chance that you have the disease, okay? Which means there's a 99,000 in 100,000 chance that you don't. Having the disease now, you can either test positive or you can test negative for the disease. And there's a 99%, the test is 99% accurate. So if you have the disease, there is a 99 out of 100 chance that you'll test positive, and there's only a 1 in 100 chance that you will test negative. Over here, if you get the same test, right, the test is 100% accurate. Again, we've got positive here and we've got negative here. Test 100% accurate. Over here, you don't have the disease, all right? So here there is a 99 in 100 chance that you test negative, and there is a 1 in 100 chance that you test positive. Okay, and what we want to know is,
You're missing some 9s on the top. It should be 99999.
where are you?
The top right
Not the
should be 99999.
Yes, you are absolutely right. You are absolutely right. Okay, so that's where we are. And what we want to do is we want to use this formula here, and we want to say, what is the probability of having the disease given that you've tested positive? Okay, the posterior probability. And we're going to calculate that by using a likelihood function, which says, well, what's the chances of testing positive if you've got the disease, times our prior probability, which is, well, what's the chances of getting the disease regardless of whether or not you've been tested, okay, divided by what is the probability of testing positive regardless of whether or not you have the disease. Okay, so let's fill that in. Up here, what's the chance of being positive if you've got the disease? Well, what you do is when you come down these branches, every time you branch like that, you multiply these together. Okay, so here, the probability of having a positive test if you have the disease is here 1 in 100,000 times 99 over 100 times, what's the probability that you have the disease anyway? It's 1 in 100,000. Over what's the chances of getting a positive test? Well, there are actually two ways of getting a positive test. One of them is to actually have the disease and have a positive test. So again, that's that 1 in 100,000 times 99 over 100. But you can also get a positive test over here if you don't have the disease. So that's 99,999 over 100,000 times 1 over 100. I'm not going to do all that maths, right? If you're interested, you can pull your calculator out while I talk about other stuff and calculate it all out. But I can tell you that it comes to quite a bit less than 1%. Okay? So the people who said, actually, you shouldn't really be worried, were actually correct. And the gentleman there was absolutely right when he said it's because the incidence is so absolutely tiny, okay, that if you test positive, you're far more likely to be over here in the 1 in 100 of the 99,999 than you are to be the 1 in 100,000 and be the 99% that's correct, okay? But what makes this difficult is not the maths, okay? We're never going to, using the Bayesian classification, we're never going to ask you to do anything that's not multiplication or addition or division, which any primary school child can do, okay? The difficulty is in the actual intuition, because both of those sides of the argument, whether it was explained by this gentleman here and when it was explained by this gentleman here, both of them sounded perfectly reasonable to me, okay? And if you miss one of these branches, then it's very easy to get the maths wrong. But luckily, there's a good tip here to know if you've created this diagram correctly. And that is, every time you branch, all of the branches must add up to 100. Okay, because these are probabilities of an event that either will happen or won't happen. So one of them must be true. Something must either happen or not happen, right? Unless it's Schrodinger's cat, right? You can't have it not quite happen, but almost happen. It's not, it's one or the other. Therefore, all the probabilities must add up to 1, okay? So if you add across here, you get 1. If you add here and here, you get 1. If you add here and here, you get 1. This was quite an easy one, so it's easy to see that we've got it all. But if you've got a really complicated diagram, a good thing to do before you go in to start doing this, to make sure that you've got all the branches correct, is just to cross-add and make sure that everything adds up to 1. Okay? And if it does, you know you've constructed your diagram correctly, and then you can go on and do this. And this, you'll never do more than add, multiply, or divide. Okay, so actually, all of this kind of looked horrible because we're looking at in an abstract form. Once you get explained, and once you see a worked example, it's actually really straightforward. Okay? Any questions before we crack on?
So does it mean that, I don't know, this sounds like, to me it sounds like we didn't take as given that we tested positive. I mean, let's say that testing for cancer is 99% accurate, and
Yep.
There's a very small chance that you have cancer because it's a
Mhm.
disease. So if I test positive, I shouldn't be worried, right?
Correct. That's absolutely correct. And in fact, I'm glad you picked cancer, right? Because cancer is a really good reason, right? So for example, in this country, we do not breast screen women under the age of 50 for breast cancer, and we do not colon screen people in the UK for colon cancer under the age of 70. And that is because if you test positive under those ages, even if you test positive, you have a small chance of actually having the disease. You're far more likely to be in an error of the test. Okay? And the reason that we don't test under this country is because you would cause more alarm, you do more harm than good. You'd be telling more people, hey look, you've got breast cancer, hey look, you've got colon cancer, than actually they did. So all these people would then be in a state of fear of alarm, and then you'd have to do other tests, and then eventually you'd find out, no, actually you don't have breast cancer, you don't have colon cancer, it's all cool. Right? So when you say, oh, are you saying that if I've got cancer I shouldn't be worried? Yes, absolutely. That's absolutely what I'm saying. And in this country, that is the very reason why we don't test for these things under particular ages, right? Because of that very reason. Okay.
Yeah, a good way to accept it is to think that if you were to test everyone out of 100,000 people, you would get 1,000 positives, but only one of them would have the disease. So you get much more false positives than real positives.
Exactly. You end up doing more harm than good. But having said that, don't feel bad if you're sitting there going, I can't wrap my head around that. I'm not 100% convinced, okay? Because there is a great demonstration problem in probability called the Monty Hall problem, which you should look up. It's to do with goats and cars, and I'm not going to go into it just now. But the point is that there is two solutions to that, okay? And it raged throughout statistical peer-reviewed scientific papers literally for years about who was right and who was wrong. And it was only when computers came along and they could actually do a frequentist test, actually run, say, well, let's do this 1,000,000 times and see which one's right, that argument was actually decided, So that is actually, professors of statistics who argue backwards and forwards about, issues of probability like this, which are counterintuitive. Yeah. Luckily, we've got computers now, so we can actually do the frequentist tests, and it's very easy to sort those problems out anymore. But back in the day before computers, the Monty Hall problem, it just raged throughout academia for years, with people arguing backwards and forwards. And professors on both sides, very well-renowned statistics professors on both sides of the argument, going, no, you're wrong, I'm right because of this, and there are other ones going, no, I'm right and you're wrong because of this piece of mathematics. Okay, so if you're sitting there going, yeah, I'm not really convinced about that, don't worry, just accept I'm right, okay? And don't worry about it. Life will be much easier. Okay.
You're right, so what's the odds that you're wrong?
Oh, out.
What's the probability that your doctor understands that?
Yeah. He doesn't have to understand it, he just has to administer the test. Provided he administers the test correctly, I'll do the probability. It's fine. Okay. So well, I said this is really easy. Classification, the actual maths behind classification is really easy. One of the hardest things to actually do is what we call feature engineering. Okay? And feature engineering is a big, posh data science term because we like to use big, posh, confusing terms because it means we can earn more money per day. I can charge you more money if I can use big words. But feature engineering basically just means what evidence am I going to use? Gathering the B's, for example, in that formula. What is the evidence that I'm going to use, and that's in feature engineering. So luckily for tweets, it's really simple. So we'll have a quick demonstration for that. We're just going to use the words. Okay, what we're going to do is we're going to start off with feature engineering just to show you everything that we could actually pull out of the tweet, or a few things we're going to pull out of the tweet. But going forward, we're only going to use the words, which makes the feature engineering really simple. But in reality, feature engineering is the hardest part of classification, right? The math, as I've just demonstrated, is really simple. Okay, deciding what the evidence is the hard part. So what we're going to do now is just go here, pop open, feature engineering. So what I've got here is a little F# script. So a couple of things we're going to do here. I'm going to use a type provider, an F# type provider. I'm going to use the JSON type provider because the information that we get from Twitter is going to be in JSON format. So that makes my life much easier. So what I have to do here, first of all, is if I look down at references, what I do here is I just NuGet in F#.data. Okay, so that's the first thing I do. I NuGet into my project, which means the DLL will live somewhere, and the DLL for that actually lives here in this nice string here that I've pasted in to make that reference into my F# script. Once I've made that reference, I'm going to open the F# data. Next thing I'm going to do here is I'm going to create a type of tweet where I actually use the JSON provider and I tell it what, let's open that a second, I closed the wrong thing. The JSON provider, and I tell it what the schema of the JSON is going to be. Okay, now in this case, I've created a document called sample.json, and I'm basically just going to create a sample document, and I'm going to point the JSON provider at that document, and I'm going to say, hoi, all of the JSON that you're going to see is going to look like this, right? And actually my sample, if I open my sample JSON file, what you can see is I've simplified the tweet because I want us to be able to see the wood for the trees. Okay, so we're only actually going to be using the name of the sender of the tweet and the actual text of the tweet. So I've gotten rid of everything else, and I've just said, look, tweets are going to look like this. All right, and then I point the JSON provider at that file. Then what I do is I load up that file using the JSON provider. And what I'm going to do here is I'm just going to show you pulling out the individual words and the sender, because that's going to be our feature engineering. That's going to be our list of Bs, for example, B1 through N are pieces of evidence. Okay, and all we do here is for each tweet in the tweet, I am going to print out the user's name, and this is why JSON providers make your life a lot easier, because once you're using a JSON provider, for example, you can just say, well, look, there's a tweet, and then, oh, look, you get a nice piece of IntelliSense there. Tweet, the user's name lives on the user, and if I could type properly, it would be great. And there's his name there. Okay, so if you've got a big JSON document, for example, you don't have to remember what part is in what. You don't have to look at the JSON to work out, which nested object you're actually dealing with. You'll get a nice piece of IntelliSense just as the benefit of using the type provider. Okay, then what I'm going to do is I'm going to take that text and I'm going to split it up into an array, and then I'm going to iterate across that array, and I'm going to print out each of the words. So basically all I'm going to do is I'm going to get a nice list of the sender and then all of the words in that sender's tweet. And I'm going to use here, which file am I using? Featureengineering.json is the file I'm using. So if we have a look at that, is that one? Yes. So here I've got Tom, Dick, and Harry, and they're sending Mary had a little lamb, its fleece was white snow, and everywhere that Mary went. You can tell I've got huge amounts of imagination for test data and stuff like that. So that's what we're going to do, and all we're going to do then is print out each of these words. So if I select that now and use the interactive doodah in F#, that is actually what it's called, the interactive doodah. So if we run just this part now, you can see, if I look up here, then what I get then is Tom as the sender, and then Mary had a little lamb, and then Dick as the sender, and its fleece was white as snow, and then Harry and everywhere that Mary went. So I've separated out now from all of that tweet data that we started with, because a tweet contains loads of data. Now I've got my evidence, right? I've said our feature engineering is going to be the sender and all of the words in the text. Okay? So that is that. Let's jump back here. But hang on, now we've got multiple pieces of evidence. Okay, over here, we just said, well, hang on, that's one piece of evidence. You know, given that this evidence, how probable is our hypothesis given that piece of evidence? But now you've said, well, we're using all of the words. That's a whole bunch of evidence for each tweet's probability. How are we going to deal with that? Well, how we deal with that is quite simple. This here, the prior probability, tells us how probable was the event before this evidence. Okay, so when we're using the very first piece of evidence, the first word, this prior probability, which actually says what is the probability, what is our understanding of the probability right now, is going to be, well, what's the probability of getting spam regardless? Okay, but after we look at the first bit of evidence, we have a posterior probability, right? Because our understanding has moved on. You know, there is a probability of getting spam or not, but actually the probability changes of getting spam or not based on this word that we've looked at. This is the first piece of evidence. So this posterior probability then becomes the prior probability for evidence 2, which will then generate a new posterior, which will become the prior probability for 3. Okay, so we just wrap around that in an iterative process until we've consumed all the pieces of evidence and our posterior and prior probabilities change, and the last posterior probability out is the probability considering all of the evidence. Okay, does everybody understand? Yes, excellent. So the fact that we're only looking at one piece of evidence here doesn't really matter, that we're then going to get a big collection of evidence. So, using that, what we have to do now is we have to train a classifier, okay, which can be quite hairy. This is called supervised learning and machine learning. Okay, we have to supervise the learning. And why we have to do that is because if you look back here, we have to know a few things. Okay, so we have to know what is the probability of getting spam anyway. Okay, we have to know what that is. All right, we need to know what's the probability of seeing a particular word in spam. Okay, so we have to know these things. All right, and therefore, the way we know these things is to train the classifier by pointing the classifier at this and telling it this is ham and this is spam, okay, and then it knows what the probabilities of this is for the likelihood of seeing these words, okay. So how we do that then is jump back here into our code. Just close these things and tidy up a bit. Yeah, you can save that. So what we want to do now is we want to train our classifier. So this is a little bit more complicated. What we do here is the same thing here again. We're just using the type provider. Same thing here again. I'm just saying here is a type provider again, and I'm saying the schema is as described previously, so you've seen that before. And then what I do is I've got a bunch of spam tweets and I've got a bunch of ham tweets. Okay, and I load those in. So if we have a look at the spam and we have a look at the ham, here for just for demonstration purposes, you can see I'm concentrating on the word bitch. So basically, for demonstration purposes, just to make it easy for you to see, any text really that contains the word bitch is going to be spam. Whereas over here, on the ham, we've got a whole bunch of guys, and this is just text. Does anybody recognize that? I just copied it out from a quite famous book. With a philosophical flourish, Catco throws himself on his sword. I quietly take to the ship. There was nothing surprising in this. No, it's Moby Dick, if anybody cares. But that's just because I couldn't be bothered generating test data. Okay. So then to train this, what we're going to do first of all is we're going to create some storage for our frequency distributions. We're going to create a bunch of frequency distributions basically. All right, and we need some storage for it. And what we're going to do is we're going to use dictionaries where the string is going to be either the word or the sender, and we're going to keep a count of how many times that word appears in each of the different types of input. Then what I'm going to do is I'm just going to basically define a bunch of functions which, working with dictionaries from F# is ugly. There's no way of getting around that. Okay. So here what we're saying is, if the key doesn't already exist, then add the key, set it to 0, and then regardless, increment that one by 1 as we pass that in. Now I want to hide all that kind of ugliness away. All right. So I'm just going to create a whole bunch of helper functions here. One to handle the sender, one to handle the word, one to handle the tweets. Okay, and then once I've done that, what I do here is you can see to handle the tweet, what I do is I take the words in the tweet, I split it up. Here, instead of just doing one word at a time, then I'm basically going to pull in the whole text. I'm going to group all the words in that text by themselves, basically. So basically, I'll have the word as the key, and then all of the words in the sequence that comes after it. They'll group them all together, and then actually I can iterate across that, saying handle that word and that dictionary. Okay, and it'll pass in this part here, and I'll be able just to say add that word and the count of how many times it was grouped in that thing together. Okay. So once I've done that, I'm going to train our classifier for spam, train our classifier for ham. Okay, so just let's pull all that stuff in there. And then once I've done that, just to make it a bit easier, again, I'll just call that bit again, like so. Then if I scoot up here so I can remember the name of these things, once that's actually done, we can have a look at the model. So if I pop down here and I say, well, show me what the spam word model looks like. You can see down here, the spam word model says, well, these are all the words that appeared in the spam. And I can do one as well for the ham word model. Here's all the words and their counts and their frequencies that appear in the spam. So basically what I've done is I've created a frequency distribution for words in spam and words in ham. So now basically I've trained the classifier so that for every new tweet that comes along, I can break down the words, and I've got a probability of whether it's ham or spam based on the frequency distribution that I've already created from the training tweets that I've got, whether they be ham or spam. And that's why this classifier inside of machine learning is called supervised machine learning, because I'm supervising the learning of my classifier by telling it examples of what is spam and what is ham. Okay? Does everybody understand? Good. Lots of nodding heads. That's what I like to see. Okay, let's get rid of this stuff just now. Let's jump back into our code. So once we've done that, we can now run the classifier against new tweets, because our classifier will now be able to understand how to classify between new tweets and old tweets. No, sorry, between spam tweets and ham tweets.
Quick question, sorry.
Yes, sir. That's all right. Don't apologize for asking questions.
Obviously, if you were doing this out in the real world, you could only do this if you had those examples of spam and ham. So if I was going to figure out whether somebody's an axe murderer, I need prior information about.
Correct. So just for the benefit of the people watching on video, what the question there was is, if I'm using a supervised machine learning algorithm like naive Bayesian classification, then I have to have examples of what spam was and what ham was. And that's absolutely correct. And that is actually the same way as spam filtering works today. Okay? Remember, cast your minds back, people who are old enough like me, 5, 7, 10 years ago, there used to be, before spam was actually fixed at your internet service provider level, all of the spam used to arrive in your mailbox. Did people remember, older people remember that? And there used to be lots of products out there that would deal with that. One of them was Spambase. Does anybody remember Spambase? Yep, it was one of the products you could use. And you installed that into your client. It was one for Outlook. You installed it into Outlook. And the very first thing that you had to do was you had to create a folder in Outlook where you put your spam. And you could create a rule, all the spam went in. Then the very first thing you had to do for Spambase was you had to point it at that folder and say, spam looks like this. All right? We don't have to do that anymore because it's been such a prevalent problem that internet service providers and there's all companies out there saying, don't worry, we'll do it. Okay, we know what spam looks like now, right? Because we've seen so much of it and we understand how it works. We've got people who collect it, and we set up mailboxes so that spam gets dumped. We set honey traps for spammers, and all the spam piles in there. So now, exactly the same process works, but instead of you having to provide the examples of spam, the companies who actually provide the spam assassins, and spam assassin is one of them, okay, they actually set up their own method of providing examples of that so that you don't have to. But just because you don't have to, doesn't mean to say that doesn't have to be done. It is done, just not by you. And this is how that would work as well for tweets. As we started off, you'd have to, as you installed our new service that we're making, you'd have to say, these are examples of spam tweets that I've gotten, right, of troll tweets that I've gotten, okay? In the future, if it became a sort of like a global problem or a problem that wanted to be solved globally, like email spam is, then there would be companies set up, probably partnering with Twitter, and they would set up honeypot accounts, just exactly the same as you would set up honeypot accounts for spam email, and they would capture the different kinds of trolling things you would get for. It would have to be set up slightly different. You'd have one for political parties, and one for gay rights, and one for all the kind of things that attract trollers. You'd have to set those kind of things up, right? But it would be done at a global level, just exactly the same way as it's done for email right now. Okay? Good. Anybody else? No. All right, so let's go and have a look then at running the classifier. So here what we're going to do is we're going to have a classifier, and the JSON that we want to classify, the tweets that we want to classify look like this. So this guy has sent bitch you suck. The other guy's just sent bitch. This guy's sent good morning, and this one sent see you later. So if our classifier works, then it should find two pieces of trolling spam, and it should find two which are okay. All right, so let's go and have a look and see how our classifier works. So if we get back up here, again, this is code that you've seen before. Actually, it isn't, because I just realized what I did there. What I did was I loaded in, I don't want to write all that code again, so what I did was I loaded in the training classifier script that I've just shown you. I've loaded it into this one, which basically means it's now, all that code that you saw previously is now part of this script. What I do then is I have to say open it. What F# will do is when you load a script like that and you give it the script name, it automatically creates a module of the same name. So you then have to load the module and say, not only did I want you to load it, but having loaded it, I actually want to use it. Thanks very much. Okay. So that's what we're going to do. We're going to do the same thing. You've seen this before. We're going to load in our tweets. This tweet, of course, it just uses the JSON provider from the training classifier script, because remember we've loaded it in here, so it's already defined up there. And now we're going to load in just to make sure we're using the right one. Yes, we're not cheating. There, I am actually using the classify.json file that I showed you previously. Then I'm going to create a bunch of, again, helper functions, because again, in F# working with dictionaries is fugly, and so we're going to hide that fugliness away in just one nice F# function when we're going to call the nice F# functions later on. So one of the helper functions we're going to get is calculate a sum of the values in the dictionary. So if we want to know what is the prevalence of this particular word in all of the spam words, then we have to know what the sum of all the spam words are. So we have to be able to count up the values in the spam words dictionary, for example. So that's what this does. What that does there is it takes in a dictionary, it takes the dictionary values, and then it sums them up and it returns them as a float, because probabilities are always a float between 0 and 100. So we're just going to return that as a float. Next piece of helper functionality that we've got, and I'm not going to go through all of these pieces of helper functionality, but I do want to show this off because it's one of the great aspects of F#. If you look here, who's used this function in C# and a dictionary before called try get value? Who's used that before? Okay, so if this was C#, it is F# actually, but if this was C#, how would you call the try get value? Right? So it returns a boolean that says true or false, I found the thing, okay? And what else do you have to do?
You need an output value.
Right. In here, you need to put an output value that says, if this was true and I did find it, by the way, it's here in this output value, okay? You don't have to do that in F#, because F# knows that that's what it takes. it knows that there's going to be an output value. So actually, you can just, in F#, you can call the try get value, just passing in the word that you want, and you will get a Boolean and the actual value back without having to put in an output variable. So the actual code looks a lot nicer. So here I can say let OK and V equal a dictionary dot try get value of this word, and if it is OK, then I will actually have the value without using output and all the rest of it. And if it's not OK, I'm just going to return 0, because obviously if the word does not appear in the dictionary, then there's 0 probability of it being either ham or spam. We said up here, everything is either spam or it's ham. Actually, that isn't true for our classifier, because it can either be ham or it can be spam, or what's the third thing it can be? Yep. The other one is both. It can be in both. And the fourth one is undefined. We haven't seen it before. So there's actually 4 things it can be. One of those 4 things, okay? But we're just actually, for simplicity's sake, we're just going to ignore it. Actually, what we're saying is, if we haven't seen it before, then there's no probability of it being ham. Okay, so I just wanted to show off F# a bit there, because that's what's one of the things that just makes it a rocking language. You don't have to worry about the output variables. You'll just naturally get those back. This will come back. Actually, this comes back. This is another cool thing about F#. This actually comes back as a tuple, but if you assign a tuple like this, if you give it 2 variables and you assign the tuple to the 2 variables, it'll automatically put the first one here and the second one here without you having to do anything, right? So actually, you don't even read this code unless you actually knew what the function does, and I do. You don't know that this is actually a tuple coming back, and you don't really care. You just say, hey, I want a Boolean and a variable and a value, and I want to call this thing here, okay? And you'll automatically get that stuff all done for you by F#. It's pretty cool. So I've got a whole bunch of other other functions like that, which are called something nice, so that when you see the code written down, it all kind of makes sense. But it's basically just all coming back to where I've abstracted these 2 pieces of ugliness from using a dictionary. Okay, and I've hidden away that ugliness in 2 functions, and we'll never have to call them again. And all these other functions here just kind of wrap those up. All right. So then down here is where we actually do the classification. It's easier when you're using F# to kind of start at the bottom and work your way up, because all the functions have to be defined before you use them. So this is actually the business end down here, right? Classified tweets. So what's happening there is we run the train classifier just in case it hasn't been called already. And then what we do is we say for every tweet that we've actually got, what I want you to do is to work out the tweet from this particular sender is spam with this amount of probability, okay? And then I want to pass into that thing the sender's name, and then down here, the probability of a given text, the probability of spam given the text, and then we pass in the text, okay? So here we start off with something really simple, so we use functional decomposition here to say, really what we want to know is, what's the probability of the spam given this text? Okay, so we just call that function. And then that function is actually defined up here by saying, well, to do that, what I have to do is I want to split out the words in the actual tweet, okay? I want to make them distinct because I've taken the decision here that using the same word over and over again doesn't make it more of a troll. You know, if you call me a bitch, right, I'm going to say you're trolling me. If you use the word bitch twice in a sentence, I don't care twice as much about it, right? It's still troll behavior. I still don't want to see it, all right? You can make this more sophisticated by actually adding, you know, the probability, by making it more probable if he repeats the word. If you feel that's more offensive, you know, it's one of these things. I don't know. Is it more offensive to be called a bitch twice than once? Is it twice as offensive as you're called? You know, it's up to you to. But here, I'm just going to go, do you know what? It isn't. If that word appears, it's just spam. All right? So we're using a distinct here. And then this is another beauty of F#. Remember what I said when I showed you that diagram? I said the prior probability, the posterior probability becomes the prior probability next time round, and we iterate across that, right? Until we consume all of the evidence. Well, here, this is the evidence, okay? Because what happens now is, when we text split, we get an array of the words. I turn that into a sequence. this is called the post forward, which basically says, take the output of this function and make it the input to this function. Okay, so you can chain in F#, you can chain these things together to create really cool pipelines, and that's what we've done here. So what we do here is we create a pipeline that splits the word, turns the array into a sequence, makes the sequence only have distinct words in it, and then here's where we do that, consuming every word in this sequence, every word in the array, okay? In that way of having the posterior become the new prior, okay? And how we do that is to use this fold. And what fold does is it says, I want you to call a function, okay? And to this function, I want you to pass two things. One is going to be an accumulator. So this is our prior probability. So for the very first time, that's going to be the probability of getting spam, regardless. All right? That's going to be the accumulator. And the second parameter, because of this pipe forward, is going to be the first word, the next word. So it's going to call this for every single word in that array, i.e. once for every word that there is, okay? And it's going to fold in this accumulator, so we'll pass this accumulator every time as well as the next word. And what we do here is we just make this the posterior, we just add it to the accumulator. So we add the posterior, and then we feed it in the next time round, and it automatically becomes the prior, and then we add it to the posterior, and it automatically becomes the prior. So this one line of F# code here does that whole calculation and making the posterior be the new prior, and then the posterior be the new prior for the next one, until it consumes every word in this array. Does everybody understand what this line of code is doing? Because this is an important line of code. Right? It's about this line of code does the entire work, basically, of everything that we're talking about. And that's one of the beauties of F#. Look how concise that code is for really what it's doing. Okay? One line. All right? So here I said before, what is this probability? What is this probability of spam? Well, actually, we'll just drop a marker down here, actually, so we can come back. Let me just drop that down here. So then if we go up and have a look at that probability of spam, all it's actually doing is saying the spam count is basically a count of all of the spam tweets I've got. The ham count is the count of all the ham tweets I've got. And therefore, the probability of getting spam is how much spam did I get as a ratio of all of the tweets that I got. Okay? All pretty straightforward. If I scoot that up. The people at the back, don't be afraid to say I can't see that. Instead of straining your neck.
No.
Yeah. Okay, so that's basically what we're doing. We're just taking that spam count as a ratio of all of the tweets that we received. And that's how we start our prior. Back down here, this is how we start our prior, the probability of spam. Before we know anything about it, before we started consuming any of this evidence here, we say that is going to be our prior probability, the probability of getting spam anyway. And this, the probability given word, we're just going to have a quick look at that. This is where we do that calculation. Okay, so what we do is we get our marginal, and we get our likelihood, and then the prior, bearing in mind that this is going to be the accumulator, because here, remember I said we pass in an accumulator and the word. That fold function passes in the accumulator and the word, where here, that's the accumulator there, all right? Everything in F#, the last line in F# is automatically the return, unless you say otherwise. The last line in an F# function is the thing that gets returned. So this is going to be the posterior probability, but it's also the accumulator, okay, which will then get passed back in at the top for the next word, okay? And this is where we use this formula. So we calculate the marginal, we calculate the likelihood function, and then we just do prior times likelihood over marginal, okay, to return the next posterior. Okay, does everybody see what we're doing there? Okay, and you see why I've used F# as I've opposed to C#. When you look at the actual formula on the board that I showed you there and use the work, you see that this is very close to what I've already drawn and worked through. Okay, because using F#, you can be very close to the maths, because in a functional language, the most granular level of code that you can use is a function. Whereas in an object orientated language like C#, the smallest granularity of code you can use as a class, because you need something to wrap it up in. Okay, so now you've got code that just gets in the way. Whereas this can be very close to the actual maths. So everything that pulls out of here is going to be every posterior that comes out will be the new prior for the next word that's pushed in. Okay, so let's punch all that into to F# interactive and then get it to classify our tweets for us. And what it says here is the probability of the first one is 4%. The probability of the second one being spam is 20%, and there is 0.8% probability of the third one and 0.8% probability of the fourth one. So it says the first two are more probable of being spam or being a troll than the last two. And just to refresh our memory, if we go back to classify, that is absolutely correct. The first two were the trolls, and the second two were the ham tweets that we wanted to let through. If we go back here, I've just got a quick question. I shouldn't have closed that down. Let me just quickly run that again. So quick question here is, bearing in mind what we learned here with this example, why are the percentage probabilities so small? Granted, much higher than the probabilities of the last two, but here, still quite low probabilities. Why are they low probabilities of being spam?
Because you have a very small sample set. You've only got one spam sample.
So that's almost correct. So what Joe said there was it's because the sample set is small. That isn't the reason. And then he went on to say, and you only have one spam tweet in it, and that's almost the right reason. But step one for that, if I've only got one spam tweet versus all of them, that means that there's a low probability of getting spam anyway. Okay, so it's the same here. There's a low probability of having the disease, and therefore the probabilities come out low. There's a low, they are in fact trolling behavior, and they say it's trolling behavior by giving it much higher probability. The probabilities are still low because actually the overall probability of getting a spam tweet is low in the first place. So all things being equal, it's probably going to be ham. Okay, does everybody understand that? And that brings me on to one of the other things that's quite hard is, once you've done this, here it's easy to see. This is significantly lower than that. So we know our classifier works. The hard thing here to do would be to set the threshold, to actually say, act upon that. Instead of just saying it's this, and showing me, you're going to have to say below a certain threshold or above a certain threshold, we're going to treat it as trolling behavior, we're going to treat it as spam. And we'd have to set that threshold. And that's something that you'd have to do. You'd have to run lots of these tests to actually see, you have to do a frequency distribution across this to actually see what the probabilities actually came out at before you could set your threshold. But the important thing is we can see there's a significant difference between the ones that it's marked as being spam versus the ones it's marked as being ham. So we know our classifier works.
Gary, can you go back to the two corpus files there, the ham and the spam?
Yes. These two.
Yeah.
Mm-hmm.
So there's two spam.
No, everything in the ham, when we're training, everything in the ham is good and everything in the spam is bad. And what we're saying here is, look, there's only one in there and there's 4 or 5 in there. Therefore, the probability is 20% of getting spam. All things being equal, right? Before we even look at the evidence of the actual spam, there's only 20% chance. There's only a 20% probability of getting spam anyway. And that is why it's a low probability. Even though it's triggered it to say, yes, this is spam, because, it was, one of them was 20%, the other one was 0.4%, whereas the other ones were like 0.08. So there's a significant difference. There's an order of magnitude. There's one order of magnitude for one and 2 orders of magnitude for the other greater than the ones that it says are ham, but it's still a low percentage. Well, that's why, because there's a low percentage of getting.
But in reality, it would be 95 or something.
Well, I don't know. I mean, how many troll tweets do you get?
What you said at the beginning, it was.
No, for email.
Oh, for email.
Yeah, for email. Oh, absolutely. If this was email, 98%. The last stats I saw, 98% of all of the emails on the internet are spam,
But
and
surely
we
with
never
the
see them.
examples, this would be a lot more accurate, wouldn't it? There's probabilities.
It is accurate.
Yeah.
It's just the probability is low. But we're dealing with low numbers, right? But to help you understand, right? Don't think of the actual value, right? Regardless of the value, think the things that it classified as the things that it classified as spam were 1 and 2 orders of magnitude larger than the ones that it classified as ham, right? It's just that the actual values of that were low. The numbers throughout are low, right? But we're still talking 1 and 2 orders of magnitude bigger. So that's a significant difference between things that it thinks is spam and things that it thinks is ham. Okay?
Doesn't this mean that if I want to hide all spam tweets from someone's Twitter feed, I also will have to hide a lot of non-spam tweets? If I want to hide all of the spam ones, I will, in the process, hide a lot of non-spam tweets as well.
Not necessarily, because bear in mind we're using exactly the same principle as is used to do with spam emails. Now, do you lose a lot of ham email? Do you lose a lot of emails that you want? Do you constantly have people phoning you up and say, I sent you an email the other day, yada, 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 and you say, oh, I never got that email?
No, but
No.
no, but in that case, there's a lot of spam. So.
But there's a lot of trolling as well if you take it globally. We're just dealing, remember we're dealing with, classroom size samples that we can deal with. But you have to remember that the principle that we're using here for making trolling disappear is exactly the same as the principle for making email disappear.
Okay, well,
And it won't be perfect to start off with. In the same way as dealing with spam wasn't perfect for email in the old days. Those who remember installing Spam Assassin and Spam Base and things like that, you'll remember the same as me. It wasn't perfect to start off with. It's a maturing industry. However, if we were going to do it globally like they did now, we'd have the benefit of the lessons that they've learned from dealing with spam.
Okay, well, let's say that globally, like in real life, like there's a low probability of you having a spam tweet.
Mm-hmm.
In that case, if we wanted to hide all the spam tweets, we would have to, in the process, hide a lot of ham tweets. If the probability to begin with was low.
Depends how good the classifier is. Oh, I see what you're saying. You said because the overall probability. So no. So if you look back at this, although these numbers are low. Let me where. I closed that damn thing again, didn't I? So the numbers were low. It was 0.4 and 20%, right, versus 0.008 or something like that, right? So the trick is, so if I set the threshold as say 0.6, okay, we would have lost all of the spam, but not lost any of the ham.
Say that again.
If I say the threshold is, so let's say it was 0.4, right? So let's say I set, so let's just make it easy. Let's say I set the threshold at 0.4. So if it reaches 0.4 and above, it's spam, right? If I set the threshold there, we would have lost all of the spam because one was at 0.4, one was at 20, gone. But we wouldn't lose the ham.
So everything above 0.4, you would say it's spam.
In this example, yes. And we would have lost all of the spam, but you wouldn't have lost any of the ham because the ham was like 0.008, so it didn't reach the bar. So like 0.08 is down here, 0.4 is here. Everything here and above goes.
Okay,
We keep
so
all of this.
What's confusing me here is that you had a tweet there that had a 20% chance of being spam.
Yes, well that's
Which
above
means
0.4.
That 80% of the time, that tweet wouldn't be spam, and you would be hiding it because it would be above 0.4.
No, because the ham stuff was all below 0.4. Right, so it's all like 0.08 and stuff like that. And every decent tweet would probably come in way below that threshold. So we're basically saying everything that hits the threshold of 0.4 and above, that is spam. We're just more sure that it's spam as it goes up. Everything that's under that, we're not really sure. So in this particular case, we'd throw that stuff away, we'd keep the good stuff. Setting the threshold is the hard thing, and we need to do more. We need to do more frequency studies to get a frequency distribution of what the actual percentages were. But given the 4 examples that we've got, we would set the threshold, say, at 0.4, and we throw away all the bad spam, and we'd keep all the good ham. We wouldn't miss anything.
Can I ask, is the mathematics? This is effectively the same question, I think. But is the mathematics as effective for identifying the troll tweets, as in, is it as reliable as identifying the troll tweets as the spam, given that the probability of getting troll tweets is so much lower than the 98% getting spam emails?
So the answer to that question is there's no way to know, because I haven't done that work. Okay, I mean, I have no idea. I don't think anybody's done that work. I haven't seen any research that tells me what percentage of tweets from Twitter are spam. So I've seen the research for email, because it's a bigger problem, it's been around longer, right? And everybody's on email, whereas not everybody is on Twitter. But you know, as we move along and there's more and more people on Twitter, we'll have it will follow the same path. I mean, this was not a perfect process when we started with email back in the day. It's pretty much, it still isn't perfect now. You still get a few bits of spam in your email. I mean, I can open my email and I can show you bits of spam. Okay, so it's not perfect now. It's a hell of a lot better than it is. It sure isn't 98%. Okay. But so it won't ever be perfect, and that's setting the threshold is the tricky bit. It's better to set it so that you get a few troll tweets in, maybe one or two. I don't think it becomes a huge problem if you're only getting one or two. I think it's when you get completely deluged in them that it becomes a depressive thing, and you're scared to open your Twitter feed because you don't know what it is you're going to see. If you're only seeing maybe 1 in 20, you can just go, oh, that guy's a dick.
It'd be interesting to know what the answer is, given your example of the medical exam.
It would be, but nobody's done that work. Yeah, nobody's...
You intuitively wouldn't expect it to work quite so well for trolling.
Correct. Right now, because not everybody's on Twitter, you would imagine it to behave very similar to the early days of email. Okay, it wasn't perfect then. There was a lot of false positives and there was a lot of faffing around. Okay, I would expect it in the early days to be exactly the same as that, but I would expect it to get perfect a lot faster than it did with email, because we'd be able to learn the same lessons as the email spam guys had learned. We wouldn't have to relearn those lessons. You know. So we're running out of time with the questions. Questions are really good, but it means we're running out of time. So. Do I really want to show this? Yes, I'll quickly show this. So what you can do, you can have a little fun with the troll. This is totally hypothetical, okay? All right? I never did this. I will totally deny it. Do not do this at home, right? But it could be, so imagine a situation where, you know, a country that might want to become independent might have a referendum. That might happen. And, you know, feelings might run a little bit high. People might get a bit carried away. And they might send you really abusive, threatening tweets that say, I'm going to come down and murder your family and burn your house down. Okay. Now you've got two ways of dealing with that. You can go to the police, or you can deal with it in a more entrepreneurial way. The advantage of going to the police is that it actually gets dealt with and that guy gets locked up. The disadvantage is the police are going to come round to your house and seize all your computer equipment, right, as evidence. Now, hypothetically, if you were a data scientist facing that problem, you wouldn't want all of your computer kit to be confiscated as evidence, so you'd have to come up with a better way of dealing with that. One of the ways you can deal with that is to go here and go to have a little fun. And for this one, we've actually got locations, okay? And what you can actually do is you can do a frequency analysis on the posts. So when you're getting tweets that come in like that, and they have threats like that, if you follow the guy, right, and he's dumb enough to follow you back, and most of them are, because then they can send you trolls by DM as well, and that's more fun too. But what that actually means is, hypothetically, of course, I would have that guy's I would follow that guy, which means I could actually follow him using the API. Once I follow him using the API, I can get every tweet that person sends, not just the ones he sends to me. And if he's careless at all, right, with his account, and he has his location information in it, then what I can do is I can use this nifty piece of code here, right? And I can grab this and I can say and as you can see, this just says, give me the tweets, I want you to group by the location, and then print that out as a frequency distribution. So if I then do that, I get a nice frequency distribution that says, hey, this location appears a lot compared to this other one. Now, if you look at that location, that frequency distribution, plus the time of day, you can kind of work out whether that's his home or his work. And if you're not too sure, what you can do is you can take that and you can pop the location into Google, and Google will map it for you, right? Which is really cool. And then, of course, what you can do is you can say, please give me the street view of that, right? And that actually gives me the guy's house, or if not his street. And what you can do, hypothetically, of course, and don't ever do this because I never would, you can then DM the guy right back when he messages you like that and say, hey, don't bother coming around to my house and burning my house down and murder my family. I'll come round to your house and we can sort it out like men, right? you will find, hypothetically, if that happens, you never hear from that guy again. All right? But of course, we wouldn't do that, because that's just being a bit silly. Now, we are now bang on time, right? So I'm afraid because I've taken questions and we've had a great discussion, which is great, but it means we're bang on time, and I want to let you guys away, obviously, because it's the last thing on the last day of the conference. So if you do have questions, either email me here, get me on Twitter here, or stay behind as I pack up and ask your question. And if you don't have any questions, then time's up, I'm afraid. Please feel free to go. But thank you very much for coming, and I hope you learned something. This is something that I came across quite recently as well. So this is some are actually state sponsored. Now, before I get into this, I'm actually going to name a political party here. I'm not taking any political sides. I'm absolutely positive that every single political party is just as bad as the item I'm about to describe to you. And the only reason I'm using this one is because it's only just happened. The next time I give this talk in a few months' time, something else will have happened and it'll be another political party. I'm absolutely sure they're just as bad as each other. But when I say state-sponsored, what I mean here is this particular instance of trolling was quite an interesting one, because it's the first time that I've noticed, I'm not saying it's the first time it's ever happened, but it's the first time I've noticed the kind of political parties and people in the public eye, organizations in the public eye, kind of using trolling, not necessarily using trolling because they weren't controlling it, but allowing trolling to kind of mask something that they've done that they don't really want the public to find out about, and the whole barrage of trolling is keeping that noise down. So what this particular story is about, and I've put this up here so you can go back and check it out later, but what happened here was Nicola Sturgeon, the First Minister of Scotland, was invited to the service of remembrance that they had for the British troops a couple of weeks ago, all right? And she didn't go. She turned down the invitation. And a lot of unionist supporters in Scotland started to tweet about, how disrespectful that was, and even if she didn't believe in the war, and even if she actually believed it was an illegal war, if that was the frame of mind that she was in, at the end of the day, she's representing the people of Scotland. She's the First Minister of Scotland. She should have gone, and that was the kind of thing that they were protesting about. And immediately there was a big storm of trolls, of people supporting the SNP, who started to write, well, Nicola Sturgeon didn't go because she was at the commemoration for the Dunblane massacre, and how dare you politicise such a thing, the death of small children, just to score political points. That's absolutely terrible. And that kind of made all of that sort of negative publicity for the SNP go away, because this big sort of army of people were making what is quite a valid point, until some people started to text back, to tweet back and say, well, look, I don't really have a political axe to grind here, but I happen to know that she wasn't at that memorial service because I was at a political meeting and she was one of the speakers. Okay, and then immediately the trolling all started again, and there was a big kind of flame war going on, and all these trolls were kind of pushing down that kind of news that, well, actually that didn't really happen. And it wasn't until people who were at that meeting started to actually tweet photographs of the First Minister at this meeting, that at that point all the trolls ran out of ammunition, obviously, at that point, because there was no argument to be had. It's like, well, here's photographic evidence. They all drifted away, and it was at that point that the SNP then released a statement to say, no, Nicola Sturgeon wasn't at any memorial, she was actually at this political meeting. But it's kind of clear that political party, and I'm not picking on them particularly because I'm sure they're all just as bad, but that political party were using the trolls that were surrounding their organisation to actually dampen down that negative publicity. And it wasn't really until they couldn't do that anymore that they kind of came clean, kind of thing. And that's the first time I've seen trolls. They're not being used, because I'm not saying that any political party controls trolls, but they could have immediately stopped that kind of abusive behaviour if they just made the statement, much, much earlier. This had gone on for days before they actually came out and made the statement. So it's not that they're using the trolls, but they're allowing the trolling activity that happens anyway for their own purposes. Okay, and that's the first time I've seen that, and so it's something I'm going to be watching more of, because I think, especially in the run-up to the general election and elections, after this and referendum after that and all the rest of it, that with political parties becoming more observant about what happens in social media, you're going to see this kind of thing a lot more, I think. So that's the kind of thing we're talking about. Next thing we want to talk about is really, are trolls dangerous? You know, I mean, is it really just text, or are they actually dangerous? So here's a couple of studies that were done, right? And they looked at these number of people, and then the investigators found that internet trolls tended to have the personality traits related to sadism, psychopathy, and Machiavellianism. So the answer to that question is yes, they probably are dangerous, but not really to you, right? They're probably dangerous to, you know, the people who are close to them, who come in contact with them, you know, every day. If you exhibit these kind of traits, you know, that you're kind of on a continuum from an annoying kind of person that nobody really likes, especially if you're quite Machiavellian, right up to, you know, if you actually are, you know, displaying sadistic tendencies and stuff like that, quite dangerous. But really, not to you if you are receiving it's upsetting, but actually it's probably not dangerous. Although these people are quite dangerous themselves, the anonymity of the internet and the fact that they're probably miles away probably means that they're not dangerous to the people they're trolling, although they are probably quite dangerous to people around about them. So, how are we going to solve this problem? Right, that's what we're going to look at right now. So, how we're going to do that is pretty much the same way, actually, is spam is solved already. Okay, because when you think about it logically, it's the same problem. Okay, so the difference between spam and ham is spam is spam email that you don't want, ham is good email that you do want. And at the minute, the latest statistics that I saw said that about 98% of the emails out on the internet are spam. The vast majority of these get culled long before they get to your inbox, okay? Your inbox does not contain 98% spam email, okay? There are one or two that still manage to get through because, you know, there's a continuing kind of arms race between the spammers and those who are trying to control spam, all right? So there's never an out-and-out victory. Well, there's not an out-and-out victory at the minute, but far less than 98% of the emails that you receive are going to be spam. So the solution that is in place for email is kind of working right now, okay? And that's the model that we're going to go with. So how we're going to do that is pretty much the same way as email spam is taken care of. So what we're going to do is, so we're going to imagine that it's our responsibility to remove troll posts, which from now on I'm going to just refer to as spam, okay? We're going to remove spam. It's our job to remove spam from any given person's Twitter stream. Okay, so how we're going to do that is we're going to hook up a process to the Twitter API and capture that tweet stream before it arrives in the client. And then what we're going to do is we're going to decouple that processing from the capturing, okay, so that no processing actually occurs on the listening thread, and we're going to talk about that, why we do that when we get there. And then the last thing we're going to do is we're going to construct, and we're going to use machine learning to construct a Bayesian classifier which will actually classify each of the tweets that comes in as either being spam or ham, and it will let the ham ones through and will do something, either throw it away or quarantine it, and we'll talk about that later, with the actual ones it identifies as spam, letting the ham ones back into the process. So that's basically the process that we're going to use. We're just going to inject a process into the pipeline that exists at the minute and do some Bayesian classification to work out which is good and which is bad. Okay, so first of all, what we need to do, enough talking, let's look at some code. We need to hook up to the Twitter process, okay? So, jump down here and have a look at some code. If I open this up, this is where I like to start. It's the simplest thing that'll work. Okay, so what we're doing now, this is a nice piece of Node script. I like to use Node for lightweight processes that just kind of run as daemons on a machine that I've got at home. You know, they take up hardly any processing, hardly any memory. They're very, very good for this kind of thing. So lightweight services on the internet I like to use Node for. And what we've got here, unfortunately I have left Rebecca Adlington, you know, you shark-fin-nosed blank, you belong in that pool, you blank whale. Right? Well, that's not very nice. Okay, so we're talking about stuff like that. Some of it's actually threatening. Okay, there's you can see here, dirty little girl like you should keep quiet, otherwise we'll publish your back history. This is something that's come about just recently. I've kind of noticed there's a word for this, and I've completely forgotten what it was because I'm a trained professional. I should have that on the tip of my tongue. Unfortunately, I've forgotten what it's called, but it's basically when a bunch of hackers get together, they target somebody, and they go back through like all your bank records and your hospital records and your birth records and stuff like that, and they create a document of everything about you, and then they publish that on the internet. You know, they threaten you, if you don't stop doing what you're doing, or you don't keep quiet, or if you say that thing again, then we're going to publish all this documentation about you. Okay, and that's become a new thing. That's slightly more than just trolling, but you'll find that the trolls will threaten that kind of thing, even if they don't really have the technical skills to bring it about. If you are, you know, a politician, or if you are speaking against a politician or something like that, or you're in the public eye and you get a threat, you know, similar to that kind of thing, that's likely to give you pause to think, because you can never tell just from that whether this guy is just a troll threatening that thing in the same way as other people, you know, threaten to come around and burn your house down. You know, there's no real threat of that ever happening. You have no real way of knowing whether they do have the technical skills to be able to do what they're threatening here. So regardless, it's still quite scary to see. Some of them, of course, are really threatening. Okay, this is one that was sent to Jessica Innes, saying to remove her name if Ched Evans is saying, I hope he rapes her, right? Well, that's got to be a horrendous thing to be on the receiving end of. Some of them come from an army of trolls, not necessarily threatening in and of themselves, but the sheer majority of them. This is actually something that happened this week. This guy, I'm not entirely sure how you pronounce his name. I would say it's Oisin Timon. This was the guy that Jeremy Clarkson punched and got sacked from the BBC for. You can see there's a bunch of fans here of Jeremy Clarkson when this happened, got onto Twitter, you know, and the things that were sent to him kind of range from, you know, I can't believe you made such a fuss just because somebody slapped you, you're such a girl, right down to down here, you know, aren't you dead yet? Which is got to be no fun at all to receive that kind of thing. So all of that kind of thing all comes under trolling, and you can see it's variously bad. There's something else that something else that I noticed. Some of them are actually quite eloquently put. You know, no wonder they have a like mind to you. You are a siren of treachery and on demagoguery. Repent, right? Just because you use big words and you're nice about it, right, doesn't mean to say it's not trolling. Okay? Just because you're an educated troll, you're still a troll.
This time.
2 minutes past 4, time to do some work. Okay, so this is what we're going to be doing today. I take it by now everybody's in the right room. Just give you a quick introduction. This is me, my name's Gary Short. I'm a Microsoft MVP. Freelance data scientist, big data architect and engineer. Usually using these kind of tools here, HD Insight, Hadoop, Pig Hive, that kind of stuff. Now, data science is a broad church. It covers a lot of things. What I actually specialize in is predictive analytics, which I did on Tuesday, and a little bit yesterday. Machine vision, which I'm not doing at all this week, and computational linguistics, which does kind of feature in what we're doing here, but we're not actually going to talk a great deal about it because we can disappear down that rabbit hole very, very quickly. So we're kind of gloss over the computational linguistics part in this. Most important part of this slide is the bit down at the bottom there where you see my blog, my email address, and my Twitter handle. Please feel free to email me or tweet me or follow me with any questions that you might have after this session. So that's me. What about you guys? How many of you guys have done any kind of data sciencey stuff before? No? Okay, a couple of people have. All right. The samples in this session are going to be in Node and F#. Anybody done Node before? Yep, a couple of people. Anybody done F# before? Okay, a couple of people. Unfortunately, different people. So it's all going to be cool. There isn't going to be anything earth-shatteringly difficult in any of the code we look at. Okay, so I'll walk you through the code. It'll be really simple. Any programmer should be able to follow it. Don't be scared with it being F#. Having said that, you should be very scared of my F# code. Okay, especially if you are an F# programmer. So this is what we're going to cover in the next 90 minutes. We'll define the problem that we're going to tackle, okay, and then we'll have a look at a way of solving the problem. There are lots of different ways of solving it. We're going to pick one, and we're going to solve that problem. Then I'm going to do a little bit about having a little bit of fun with the trolls, something that we're going to talk about hypothetically, of course, something that I would never actually do, something that I don't recommend you ever do, all right, but we'll look at it from a hypothetical point of view. And then at the end, we might, depending on how much time is left, we'll have a lot of discussion about something a little bit more sinister than just trolling and how we could adapt what we've learned whilst we solve the problem of trolling to this new kind of sinister problem that we're going to talk a little bit about at the end, depending on how much time we've got. So first of all, defining the problem. What is it that we're actually talking about here? So we're talking about trolling, and trolls. Some of them are just purely insulting. So here was one that was sent to